Welcome, Advent Coders. It is day 5, and I already solved this yesterday. And as you can see, my times were kind of long. This was a tiny bit more of a tough challenge. The rank doesn't show that it was too bad still, but so yeah, it took me a while. First part was half an hour. The second part was 2 hours. I had a working-ish solution a bit earlier already, but it took me a lot of debugging and stuff, so it just took forever. Plus, I'm not feeling too great, so I didn't actually record my face, and even now I won't do it. I'm trying to just recover. But I still want to show you through the code and what my thought process was, and maybe that helps you as well. So let's get right in. So I had to actually separate this between solve 1 and solve 2 because it makes it a tiny bit easier. And down here we have the input, the example input as per usual. I had to split all of that out, which is fine. But so what's the task? What was actually the task? Bada bing, bada boom. So we have been given these seed numbers, okay? They all just have a specific values. And then we need to transfer them into a location value. And to do that, there is a whole bunch of tables here that tell you exactly how you transform them. So you transform one to another, to another, to another, to another, to another, to another. Now the trick here is, what do these numbers mean? So these seeds are these are 4 different seeds, at least in part 1. Okay, and then this part, what it says is we take the from the seed. In this case, it would be if it's seed to soil. This is seed, this is soil, and this is the range. So essentially, seed numbers 98, 99, and 100 are being transformed into 50, 51, and 52. Same with the 50 to 52 with a range of 48. And then once you transform the seeds into soil, then you do the same from soil to fertilizer. It's the same thing. And until we get all the way to the location. And then the question is, what is this nearest location that we need? Which in this case would be 35 in this example. Now, the trick here is, you could just translate this into, hey, 15 is 0, 16 is 1, and so on. And here it seems like it's fine in the example, because like the biggest number here is 70. So that seems to be fine. Except once you realize that in your input, you're working with 100 million numbers. So that is not a feasible thing. If you did that, you would definitely crash it. And that is, again, the point where, hey, don't just brute force and replace all of them. No, you need to be smart about this, right? To do this. And there's also way more seeds here, and so on. One last thing, if your seed number or whatever number is not mapped on here, it stays the same for until the next process. So there's certain times when then, hey, the 14 does not get translated into anything else. In this case, it doesn't, because, hey, there's no 14 anywhere here. So the 14 will just go down to this part, which is then going to be captured by this 0 with a range of 15. And then it's going to be transformed into 39 plus 14. So, yes, that's part 1. So, how did I solve part 1? This time I didn't work by lines, but I used my words, my little words thing here, because what it does is it actually doesn't just separate it by lines, but each individual, like, it splits it by spaces as well, and that way I already have everything split up without me needing to worry about it, which is very helpful. So I then go line by line. Now what we need to realize in our input is that there's always a gap. Okay, the gaps help me to realize, hey, this is actually a new table now, and then this is a new table. So what I've done is I'm going to say, hey, I'm working with states. If the length of the line is 0, then the state increases. That's pretty nifty, right? And then I do a whole bunch of other stuff that I get to in a second. So if the length of the line is 0, because there's a gap, then, hey, we are in the next state. In that way, what I can do is I can say, hey, the state is 0. Okay, great. Now I'm grabbing my seed values. So in the first line, I take the words that are not the first word, because the first word is just seeds. So I want all the other words that are not that, I transform into an integer, make them a list, and then I have my new values. Now I have a little system here that I worked on that, because now it doesn't go into this, it goes around, the line length will now be 0, and now it transforms new values into old values. That way we can then work with the old values, transform them, and also check, hey, is there anything left? So what happens? For I in range of the length of new values. So for each new value, we say, hey, if the new value is none, that's going to be important for the later where there's no mapping. Then we say, hey, new value is actually last value on I, right? So we're just filling out the nons with the last values because they're not getting transformed. And then I say last value equals new value. And then I say new value is just none times the length of last value. And that's it. That helps. And that way I'm always swapping new value and old value, and I can keep transforming. And the cool thing is, I really don't need any more states. I just need to say, hey, state is not greater than 0. That's all I need. I was thinking for a short moment that I wanted to write them all into a dictionary, all of the tables into a dictionary, and put the state number as the index for each table. But then I was like, I don't actually need that, I don't think. I can just do it inline, which I was able to do. So that's nice. So if the first word is not numeric, then continue. Why is that? Because there's always the headline where we have a non-numeric word. Well, so that's good. Then we can just continue. And except of that, we will always have 3 values. Always 3 values. So I would do the C2. I don't know why I did C. I really don't remember why I wrote C. I just needed to do it. The change to, change from, change length. I don't know. Something like this. I just couldn't write to, from, and length because the to and from are keywords. And then they're just the integers of those words, 0, 1, and 2. That's as easy as it is. And now this little thing does all the magic. This is really where the magic happens. I enumerate my last values, I and V, and then what I say is, and the reason why I didn't need to do that, I don't think. Yes, actually I did. The way that I implemented didn't need to, because the whole non stuff. If that index is none, then I want to take it from the previous one. Could I have done it in a different way? Probably. But I took C from, if that is smaller equal the value, which is smaller than C from plus C length. Which means if our value is in the range from the C from and the length, which essentially show the boundary from the beginning to the end of the transformation. If that is the case, then I take the value and then I add the difference between the C2 and the C from, which is just the offset. That is just the offset. So let's look at the example down here again. If we're going from 15 to 0, then it means my offset is minus 15. That means if my seed is, let's say, is 16, then now I need to go to 1. If it's 17, I need to go to 2. So the offset is 15 in that case. And that's what I do with this part here. And I just assign it to new value. And that's it. Every time now, it will try to go through and try to do the change if it can. Which is pretty nifty. I assumed, obviously, and that is key to realize in production, because this is not production code, this is a challenge code. But what to realize here, if you were in production, is, hey, there could be overlap. Like, somebody could have, some of these values could overlap, theoretically. I assumed successfully that there wasn't overlap, which makes it easier for us to code. So once all of this transformation has happened, what I do is one last time, I check if there's any nons and replace it with the last value. And then I just return the minimum of the new values. And that's it. That's part 1 solved, which is pretty helpful. Now, part 2. So this first part took me half an hour. This next part took me 1.5 hours. And I was thinking for a little bit, and it's like, working on this, I need to copy it. So I copied this stuff because I needed to have a slightly different approach, and I didn't know how to combine these things. So, what does part 2 do? In part 2, these seeds are not just individual seeds. So we don't have just seeds 79, 14, 55, and 13. No, they changed it that we now have seed ranges. Seed 79 with a length of 14. So it goes up until 79 plus 14 minus 1 to 92. Same with 55 plus 13. That is up until 67. So suddenly we were dealing with ranges and we're comparing them with other ranges. And this is where I had to wrap my head around for quite a while. The question was still, what is the lowest location number? But now we have a little bit more complicated. And here's what my solution looks like. I had to create essentially 2 more functions here. Okay, so what I've done is I still work with the state, so stuff is similar. But what you'll notice is that our main function at the time is smaller. So I now say state 0, I need to not just run all the seeds. I now need to change what it's like. So now I'm actually making a tuple with the starting location and the length. So I'm creating these pairs here and add them into values. I don't need last value and new value because I'm all doing it in the process step function now. So here first I'm creating the values. Then once we are at each step, what I'm doing is, again, if it's numeric, don't do this. And then I create a transformation list that has all the transformation lines in here, and just store this. So that's what I'm doing here. And then if the length of line is 0, that means we're in the next process and we have all the data that we need to transform the seeds because we have all the transformations matrix. So state goes +1 if state is greater than 0, because I don't want to do this after this part because we don't have anything to transform it. What we then do is we replace values with process between transformation and values. And then we say transformation is 0 or nothing again. And then we grab them again. And then at the very end, we do it one more time, and then we return the minimum. Here, the minimum, I need to pay attention. These are tuples. So again, I mapped then the values and only took the first value. Because here's the logical thing. If you have a range from starting and length, anything that is greater than starting is not smaller than starting. So all the starting values will be the ones that are potentially the shortest. So that's all I needed to do. Compare the starting values and take the minimum out of them. So what does process step do? So the idea here is this. We have values, our old seed values. These are ranges. And then we have our transformation matrix. And then we process it and get new values. Then we have a new transformation matrix, do process step and get new values until we have done that with all the states. So how does the process step work? We have new values, and then obviously old values, like we had before. And what happens, and this, again, this is where I tried a few things, didn't quite work, I had to rewrite it, and it just took me a while to wrap my head around this. If the length of the values is greater than 0, we keep going through them and process one value at a time. It's a value pair, really, right? So while the value is greater than 0, why am I doing this instead of a for in loop? Because we're going to be adding two values. And I'm going to show that. So we take the first value. We're going to say did transform is false. And then we go through each of the transformation tables. Now, what I need to do is I have a split range function that then checks our range and compares it to the transformation range. And there's a couple of different things that can happen. We can have a full overlap, we can have a partial overlap in both directions, we can have no overlap. So what we're getting out is a transformed and a not transformed section. We're splitting our range into parts so that we can then say, hey, this one has been transformed and this one has not been transformed. If we're just getting back not transformed at all, like if nothing has been transformed, all of them have not been transformed, we're just going to keep going. If at least one part of it has been transformed, then, which I find out with the length here, then I say did transform is true, new values extend transformed, because that has, I'm already offsetting it in this function. And the values, which is all the old values, now extends the non-transformed. So we now still have a section that has not been transformed. And we might find that in a different section, potentially, in a different transform t, which is okay. But if we don't, well, then what will happen is it will be not transformed every single time through all the t's. Did transform will stay false, and then I say new value should append v. So if this current value has not found any transformation table that it can be transformed with, not even in part, then I know it doesn't get touched by any of them, and we just take the old value and put them in. And then we remove the first value, because that's the one that we looked at. And then we return the new values. And that's it. Now, because of this splitting, what will happen is that we will get more and more values in our more and more ranges that are smaller and smaller, because they get smaller and smaller dissected. But it's still better than doing every single seed individually. Okay, so now, last thing, what does split range do? And this one I had to completely rewrite that like twice, because just this whole getting the whole comparisons exactly right was a headache. But how does it work? I get my original, that is the values, and then my transform matrix. What I say is I create two parts transformed and parts not transformed. There are just two lists that will be filled with the ranges, the smaller ranges, right? I also already calculate my offset, which is the transform 0 minus transform 1, like we found out above in part 1. That is as easy. And then I go through all of the different cases. Is there probably a better way to do it? I saw somebody they just didn't actually check for the cases. They just calculated the parts, and if there's no part, then it just left it. That works as well. That would have probably been saving me a lot of headache, but this is what I did, so I'm gonna go with it. So it goes through all of the cases, fills up parts transformed and parts not transformed, and returns it here at the end. So what are the cases? First case is that there is absolutely no overlap. If that's the case, parts have not been transformed. The original is just gonna be pooped back out. So when is that? When the end of the original is smaller than the beginning of the transform, or that the beginning of the original is bigger than the end of the transform. In that case, it is completely outside of the range. There's also the case that there's a full overlap. A full overlap is if the original beginning is greater than the beginning of the transform, and that the end of the original is smaller or equal to the end of the transform. That means it's inside. Okay, if that is the case, if it's a full overlap, that means all of that gets transformed. So I'm creating a new range here with original 0, that's our original address, plus the offset with the original length. That's it. Now it gets a tiny bit more complicated, where we have different types of overlaps. The first one is split both ways. That means that our old values are overlapping the transform in both directions. That essentially means that there's a full overlap the other way around. That's really what this is saying. That the transform is now inside the original. So the transform beginning is greater than the original beginning. And then the transform end is smaller than the original end. It's the other way around from up here. And in that way we know, hey, there's a section before the transform that doesn't get touched. There's a section after the transform that doesn't get touched. And then there's a section exactly in the transform that gets completely rewritten. So we calculate our 3 lengths. Our length 1 is our transform beginning minus our original beginning. By the way, transform 1, it's the same thing again, right? This one is where it goes to, this is where it comes from. So we're always comparing this and this, right? So the transform beginning minus the original beginning, that way we know the length between those two. Then length 2 is just the transform length, because it's taking up the whole space. And then the trailing length is just the original length minus L1 and minus L2. So parts not transformed is original 0, because we're not changing the, we're not offsetting. So it's just the original address again with the shorter length. So we've just split this. Parts not transformed is also the original, but this time we want to start at the trail end. So we say L1 and L2. We add those to it because it should be at the end of this. And it's with the length of L3, whatever is left over. And the parts that are transformed are, we can just say transform 0. We don't need to do an offset here because it's all of it. So it starts at transform 0 with the L2, which is really transform 2. And that is the part transformed. Now we have the 2 cases where we have the trail is out and the lead is out. The last comparison I need to make is if the original start is greater than the transform start. We've done already all the other cases. So this case is should be the only one where it says, hey, I'm inside, but not completely, because this one has not caught it. So we get the length, which is the start of the transform and the length of the transform minus the start of the original. See, even now I can't wrap my head around why I did this that way. It makes sense though. Yes, because the original, yes, it's the end of the transform minus the original. That is the length 1. Yes. So parts transformed is the original plus offset, and then by the length of L1, because it goes from wherever the original starts to the end of the transform range. And then we have the parts not transformed. That is the rest. So original plus L1, that is whatever the rest is. We're not offsetting. And then we say original 1 minus L1. So the original length minus whatever length we used in the first part. And then we say one last thing. We now calculate the length is the, I think we did it similarly up here somewhere. Yes, right up here. Because it's the lead part that we're missing. So it is the beginning of the transform minus the beginning of the original. That is the length. So parts not transformed is the original without any offsets. And this shorter length. And the parts not transformed is now the original plus length 1 plus offset. And then, which technically I guess I could say transform 1? Transform 0 actually. That should actually do it. But it was working now, so I'm going to leave it. And then the length is the original length minus whatever we used already. You can hopefully see why I had a little bit of a struggle here doing all of this. And why I had to debug so much and what a big headache this was. And if you look here, if I print out VT transformed and not transformed, that was one of the debugging stuff that I did for a while. And I did it with the examples here. You can see partly exactly what happens. Here is a good example. I have my value 57 and 13. And here is the range. Is the transform. So 57 is greater than 53. So I know that it's at least, and it's smaller than the end of this. So there's a partial transform, which we see because it's been split into two. This one range is now split into two smaller ranges. One of them will be said, hey, that's a new value already. And one of them will be like, hey, check me out in case there's another transform that can be used with me. If not, then you just put me into new values, as we did up here, right? Did not transform new values. So we can check here, is that all correct? So 57, 53, and the transform is 4. So this is a difference of 4. So 53 minus 57, 57 minus 53 is a difference of 4. So this one is 4 into this range. And because of the offset is minus 4, it's back at 53. Perfect. Now, it's 4 into it, and there's a length of 8, so we can only use 4. So, boom, 4. Perfect. So we know the transform is correct. It takes this section here that is still available, and anything else is outside of the range at the end. So it's now going to be 61 because it's at the end of 53. 53 plus 8, 61. And it's with the rest of the length. 13 minus 4 is the rest of the length. So it works. It works well. Have I ever... In the example, and this is another thing, in the example there was never a case where I had a two-way split. That is the case, though, in my input. And so I had errors there that I didn't catch in my example. That was another issue. And yeah, it was a bit of a headache. It was a very interesting challenge, but just tedious to work through. Now, I like my code to be kind of usually compact, and I like my solve to get both answers, so I rewrote this a tiny bit, where this transform seed is essentially solve 2. Okay, so transform seed is solve 2. And you don't have to do this, but I just like to do this. And what I did is I said solve. I already do the words here. I take out the seeds with the integers out of the very first. And then I say seeds for part 1 and part 2. So what I'm essentially saying for part 1, hey, create me a tuple with a range of, hey, the seed number and a length of 1. Because that's really what it is. And then I say, hey, every other, make me a seed couple with the start and range, like we had in the other part. And then just do the transform for me in both cases with those words and the seeds part 1. That way, transform seed, which is, like I said, solve 2. I don't need solve 1 anymore. I can take all of that away. I don't need to do state 0 anymore. And actually, I don't need any of this anymore. I don't need the state anymore. I don't need any of this. I don't need state. So that makes it a lot easier. I don't need to create my seeds here because I've already done this. And because of the continue here, this is not going to hit if the line is 0. Perfect. So this should still work. Yeah, those are the values for me. So yeah, so all I've done is essentially I use the slicing method from the second solve to also work with solve part 1, because that way around should work, the other way around it doesn't. I just needed to make sure that my input, my seed part 1, is adapted to the new values. So I made a pair out of it, and that's it. And I don't need states here anymore, so it's actually a tiny bit faster. And it still does the whole process step transformation stuff. So I went from 171 lines to 138. I saved a few lines. Yeah, I hope this was helpful, and I hope you enjoyed this. And maybe you were able to solve it, maybe you're not. Actually, I was almost ready to give up and try again the next day, but I'm glad that I didn't. I'm glad that I stick to it. And yes, I'm gonna see you tomorrow for the next challenge. Auf Wiedersehen!